and he has various skills in different areas. It's like innovation and intellectual property, digital and industrial point zero technologies, change in management, etc. So I'm going to invite our resource person to the section and all the participants on behalf of Department of Mechanical Engineering. Thank you.
So then, sir, it is up to you, sir.
Thank you. Okay, thanks a lot for a nice introduction, and thanks for inviting me for this session. Let me just cast the presentation first over here, and please let me know once you are able to see my presentation. Are you able to see the screen?
No, sir.
No, sir.
Just a minute. Is it visible now?
No, sir.
You can share the
I already
entire.
shared it.
Yeah, now it is. Oh, now it is okay. Sir.
No.
Okay, fine. Before I start, Dr. Shanmugesh, within the present, yeah, I will do that. Before that, just requesting, if anytime you are facing a difficulty in transmission of this presentation, just let me know through chat
Sure.
or so, any other means, so that then I will either stop my video so that then the transmission is good, and then I will open my video at the end of the presentation during the question and answers.
Sure, sir.
Is that okay?
Fine, sir.
Okay, so let me start the presentation. And so as it was introduced, it read as IoT and manufacturing. I have a bit tweaked it, the topic, saying that it is I 4.0 in manufacturing. And I will also talk about the reasons behind it. So before that, let me welcome all the attendees to this session. And thanks for inviting me. Let me start with the topic here on. I'm believing that you are able to see the next screen. Are you able
Yes,
to
sir.
see the next screen?
Yes, sir. Fine, sir.
Okay, thank you. So it reads digital twin as a title, and I will talk about why I'm talking as a digital twin in initial some of the slides. The bottom tagline talks about human being evolution, and I think if all of us understand a bit of it, a digital twin and a perfect example of a digital twin is a human being evolution. And I will also talk about this in a couple of slides in the initial period of my presentation. You can read one of the caption on the top side. Experience is not what happens to a man. It is what a man does with the experience that happens to him. And that is very well predicted. If you see, when a human being is born, and when it is a youngest toddler, it is just touching and feeling. And before it starts touching and feeling, it is just listening for the initial 2 months. And nothing but the brain mapping is taking place during that period of initial 2 months when a kid is born. And what is happening is all the brain, inside the brain, there are all the learnings that are getting mapped. And when I say mapped, it is actually creating a memory. Initially, it is a short memory, then it becomes a long memory, and then it becomes a subconscious mind as well. If it is not used, it remains in subconscious mind. If it is used, it actively becomes one of the experiences that has been learned by a human being and which is being actively practiced. And this is how a human being, when it is touching, feeling, experiencing the vibrations from environment around itself, it is mapping its own brain. The learnings are getting mapped and it is utilizing it. When it utilizes it, it again ensures that whatever it feels in new sense is again remapped. So it is learning and learning and learning. And this is what it continuously closes the loop. It forms a circle. So whatever is the physical world that a kid is experiencing with, there is a back-end world that is getting mapped inside its brain. And this is what is digital twin. And this particular phenomena is what today the scientists or the researchers are trying to create in a non-natural world, which we call it as either it is an industry, either it is a business, whatever form we might call it. But this is what is happening to the technology, wherein we talk of deep learning, machine learning, and so on and so forth. Let me go on to the next slide. This is what we talked about: gathering, analyzing, creating, and acting. And this is actually how the human brain evolution has taken place. If you're able to see and understand this picture, the human being is holding its brain in its hand, but what does it mean or depict is the evolution of brain is taking place constantly throughout its life, and it's the digital twinning process is constant. It never stops throughout the life of a person since it is born till its death. And digital twin, if it really happens to its sense that I talked, then that would be the real Industry 4.0 experience. And it might go on to Industry 5.0 or so onwards as it would evolve further. Now I'm changing my topic to Industry 4.0 from digital twin, because digital twin is what is going to be an essence of Industry 4.0. And that is where I started my presentation with digital twin. When it comes to experimentation, it's Industry 4.0, because we are people from engineering backgrounds. We are working in industry or we are working for industry. And that's where it would be in real sense, in practical sense, it would be an Industry 4.0. The title reads artificial intelligence outside the bracket, and inside the bracket, it reads machine learning, deep learning, data analytics, industrial Internet of Things, and cloud computing. In broader sense, I have not written big data and some other things because it comes under data analytics. But then a bigger umbrella is artificial intelligence. If natural intelligence is what a human being, and artificial intelligence is something that is getting copied from the natural world in the industrial world, wherein machines are being experimented for making them more and more intelligent and smart. That is where we call it as artificial intelligence. And artificial intelligence is nothing but, as I talked in a couple of slides initially, learning. When it was learning for a human being, it was simply learning. But when it is for machines, it is machine learning. But then machine learning does not stop over there simply. It has to be more and more smart. It has to learn itself. That is where we talked about a toddler touching and feeling and mapping its brain automatically, actually autonomously. And when it is autonomous state, not an automatic state, it's deep learning, a neural linguistic learning. How is it enabled? It's enabled with gathering the big data and computing it. Computing, because it's a big data, it's enormous data. You need cloud, big servers. Whether you talk of, and I would not touch upon edge and fog and cloud, but I'm simply terming it as cloud. Cloud computing, enormous computing taking place within cloud, which is a hardware infrastructure enabling data analytics to take place, which is further enabling deep learning. And that is how artificial intelligence takes place or would be taking place. And the data transfer, the incoming data and outgoing data is enabled through a hardware infrastructure which is wherein industrial Internet of Things and the so-called devices comes into picture, which we call it as gateways. So Internet of Things in a broader term is definitely which is going to utilize internet speeds at enormous speeds and computing at enormous rate, which is where a softer side of it is playing a role through satellites, through Internet of Things gateways, and which are enabling cloud servers to compute, which are enabling further artificial intelligence and artificial intelligent devices that would also be utilizing this phenomena, such as collaborative robots, augmented reality devices, virtual reality devices, which in broader term today is being called as extended reality. And I will a bit of touch upon this term in my slides when I would come on to extended reality. So we all know first revolution, second, third, fourth. First was mechanization, steam. Second was electricity. Third was computers in 1969-70, and cyber physical in 2005-2008 time frame, wherein we started talking of internet. Actually, in 1980s, in 1990s it got stronger. Actually, the term came into place somewhere in 1999-98, and which got evolved. And most importantly, this is what has or would make it more stronger, or has been making it more and more stronger as we have evolved from 1G to 3G. Predominantly in India today, we are at 3G, not 4G really in real terms. Jio has made it happen. Then it was Airtel, but Airtel did not have a hard infrastructure. Jio came in with the harder infrastructure. But today we say that we are embracing 4G, whereas 5G is a reality in some places in the world, but it would take a longer time. It came into existence a decade before. Not much of it is being yet talked about. But 5G will be very, very, very important for a real Industry 4.0 to happen when we say that real-time information is getting transmitted across at once. Now, we all talked about all these things. What are the layers which are important and which you will see in the industries that would enable a Industry 4.0 to be established in its real sense? It's a perception layer, which I personally call it as digitize. There are so many devices and much in action today in industry. RFID are so long being talked about, 3-4 decades before or more than that. Readers, cameras, again 5 to 6 decades before, but industrial cameras came into existence 3 to 4 decades before, getting more and more smarter now. GPS, WSNs, different kind of sensors wherein vibration, temperature, pressure, pollution, and so on and so forth. And we'll talk a bit of that as well. All these sensors, all these devices, when they are attached to an equipment, to assembly stations, to machines, that they will be enabling the machines to talk to an outer world, whether it is for different parameters such as temperature, pressure, vibration, rotations, reciprocations, so on and so forth, that it will in real sense start transmitting the data in its real sense. When it starts transmitting, there has to be something which catches it and further transmits it, wherein again the internet comes into picture, Bluetooth devices, Zigbees, Wi-Fi's, near field communications, LTE is becoming a little bit now old, but then it is required in some cases for sure. and this is where a connect piece will come into picture, which has to gather the data from the devices, sensors, from the machines or equipments, and then in turn has to transmit it through internet gateways, IoT gateways, to the cloud, wherein then MQTT, AMQP will play its role, because these are very important, so that they have to adapt to different protocols from the receiving side and towards the transmitting side. And this is how it will make it more and more smarter, because when you start analyzing the data and then throw it back, it will create autonomous state. And this is where the IoT technology stack architecture gets its shape. Hardwares, softwares, communications to cloud, and then the cloud application, that is analysis, throwing it back again to the receiving people, like the management, the leadership, so on and so forth. Till now, I hope it is clear. I would take a moment and ask if any questions or anything that you want me to, if you want me to modulate my speech or speed or so on and so forth. Is this okay with Dr. Shanmugesh and team?
Yes, sir.
Or if
Fine,
anybody
sir.
has any input for me?
Fine, sir. It's good going.
Okay,
Fine, sir.
thank you, team. Let me go on to the next slide. Now you see that the topic changes. It's digital twin, and I'm talking of digitize. Now there are so many devices. We are using USBs, there are RFIDs, active and passive, there are Wi-Fi devices, there are Zigbee coordinator is there, which interacts with the routers and then in turn interacts with the end devices. Very important, Zigbees play a very big role in the industry, wherein there is a small area which needs to be interacted with. Then there are near field communication devices, wherein one might wear bands, wearables across the body, and wherever they are passing through, the near field communication devices might interact with each other, and then the communication will enable to transmit the required data, then analyze it and take appropriate actions. I will talk about this in some of the examples use cases. LoRa, if you have heard of long range devices, which are very important open communication protocols, which can be used very extensively for smart cities, and in some cases the facilities, wherein it covers 2.5 miles of square kilometers, square miles, and it can interact the data within. So typically a bigger factory like Tata, Bajaj, John Deere, and these, they are spread across 100, 200 acres of area. LoRa plays an important role because it can catch signals from all the corners of premises within a factory, and then it can interact with IoT devices with cloud, throw back the data, and on the screens, bigger screens, the leadership can visualize real-time data continuously. So these are some of these devices, vibration sensors, pressure sensors, and so on. These are the ones which are going to digitize an industry or a factory. Now, how a typical EF architecture should be in a factory? So let us assume this cube is a factory. In a factory, there are manufacturing processes, and in a bigger sense, facility maintenance is a bigger area. So there is water harvesting, there are effluent treatment plants, sewage treatment plants, water treatment plants, water reservoirs. Then there are energy harvesting systems, solar panels. There are transmissions, electricity transmissions. So in some cases you might find 11 kVA, 132 kVA power substations installed within a factory. So all that facility maintenance is a bigger infrastructure vis-a-vis manufacturing processes inside, like assembly, machining, fabrication, welding, painting, and so on and so forth. It requires supply chain, material inflow, the finished goods outflow. In addition to this, The local administration has to take care of safety of people, health of people, environment friendliness. So the pollutants or emittents should be as minimum as possible. So there has to be infrastructure. Then there are allied departments like human resources, finance, and others. And order planning is continuously taking place, production planning, and then sales and marketing is continuously in communication with factory to and fro and making the sales happening outside the factory premises. So this is what is a typically a value chain of an industry. Now let us talk about the plant level architecture. We talked about digitize the perception layer, then the communication layer, and then the final layer. Digitize, connect, and then the analysis in the earlier slide. Within a factory, digitization must be there in its first place across the manufacturing and facility. The assembly line, machine shops, compressor rooms, generating sets, transformer rooms, and so on and so forth. All those must get first digitized. So sensors, RFIDs, ZigBees, PLCs, programmable logical controls, hydraulic circuits must be digitized. The pneumatic circuits must be digitized with, let's say, pressure or temperature, in some cases, vibration sensors. There are many kinds of sensors, strain gauges for that case as well, for vibrations. All those with advanced technologies must be digitized based on what one would like to access a data into. For example, somebody wants to continuously access data, whether my line is running continuously, whether there are breakdowns. What is a breakdown? Where is it? How can it be fixed? When will it get fixed? Prediction. All these kind of decision making first must get jotted down on a paper. What do one would like to digitize? Accordingly, digitization must take place. Once the sensors are in its place, then the correct piece. Now, how much security protocols are important? Whether the IT infrastructure within a factory is encrypted so that outside world is not easily able to interact with unless and until the company protocols are extended outside to the marketing sales team, to the sales and purchase team, or to some of the tier 1, tier 2 suppliers that you allow, authorize to interact with the local infrastructure, with the securitized infrastructure. So that has to be designed. So wireless and wired communications, Ethernets, Internets, LoRa devices, those must be designed and that architecture must be put in place. And then the final piece comes into picture, which is analyze. Vis-a-vis, keeping in mind that how much data is going to get analyzed and in next 10 years or 15 years. So a stackable IoT gateways, mod buses, whether it is AWS or Azure clouds, local servers, so that is edge and fog, and then a bigger cloud, a bigger server. Within the premises, outside premises, if it is a bigger corporation, there are hundreds of factories, 50 factories, 20 factories within a nation, outside a nation. Where would you like to place that server wherein it would interact globally all 24 hours? This architecture, IT cell must, keeping in mind, must put in place. And that piece must be then implemented and executed. This is how a plant level architecture would look like. Its perception layer, its communication layer, its analysis layer. Digitize connection piece and then put the servers in place, which you would like to work with. Now, this is what is the plant level architecture. All these three should talk to each other in at consistent time. It should be dynamic. Once it is dynamic, then in real time, the information flow to cloud and from cloud will take place. This will make it a perfect digital twin that I talked in the initial period. And this is what is a plant level architecture requirement. I hope it is clear. If you allow me, we can go into the next slide. Is it okay?
Yeah, fine, sir.
Okay, thanks. Now, as I ended my earlier note with digital twin, how would it look like? See, the production planning, the people are continuously planning the orders, they are continuously modifying the orders, and then they're finalizing and they want to sustain it in a 8 hours of a shift. What happens is that there are so many parameters which are changing the plan, environmental, outside. There is a breakdown on the machine, there is a breakdown for the trucks, there is a strike outside, the roads are not working, there is a heavy rain, heavy fog, enormous temperatures, not enabling, disenabling the continuous transportation, the communication to take place in its continuous sense. These are the bottlenecks they have to overcome continuously, and so they plan, they modify, ultimately they finalize, and then they sustain. Similarly, the material flow and the finish outgo. The people have to continuously assess whether the material is coming or not coming, what is the problem. Then once it comes, they acquire, and then they ship it to the line, the assembly line, the machine shop, the paint. They have to continuously confirm that the over inventory does not take place because it costs in crores, and it should timely also ship to the customers, the finished good. So they are continuously working on this. So what does it mean? They have to continuously ensure that the decision making is so important for the production people, for the material people. And ultimately, the manufacturing people, based on whether the plan is firm, whether the material is finally coming, then they have to ensure that all that has taken place and they launch it and they produce it. And in turn, they have to also ensure that the machines are not going under breakdown once they receive the material. The processes are safe, people are safe, all the resources are available, and ultimately they produce a quality product. And when they ship it, they must be able to trace if there is in case a problem on that product for a customer, they should be able to trace back where was the route. So this is what is a typical manufacturing process, whether it is pharmaceutical, whether it is heavy industry, whether it is machinery industry, whether it is any industry. This, if has to be more smart, Internet of Things come into picture, digitize, connect, and analyze, and a digital twin will make it more smart. All these bottlenecks can be taken into consideration, and accordingly, the decision making must become autonomous, not automatic. Today, we are making automatic decisions in many cases, but autonomous. And this is where the industry 4.0 in its true sense will come into picture. Now, let me talk about some of the use cases from industry, wherein I personally worked upon, implemented. In some cases, I know that what industry is doing. So let me talk about some of these things. Now, safety and environment is the predominant compliance towards society and for the government, and so is for the management. There are so many infrastructural equipments which are functioning 24 hours, 365 days in a factory. Compressor rooms, gensets, and so on and so forth. Person has to go on an everyday basis on preventive checks, and they are not able to predict every time. Now, herein there is a small example. If the factory installs a LoRa node, LoRa gateway, which interacts with IoT gateway and in turn with the cloud, and it is picking a signal from the people who are working on different equipment across the premises. They are spread across. Their safety is predominant. Once in the morning, the person goes to a particular station, he should come back safe. Let's say he enters into a genset, a bigger genset room, and then it catches a fire. What? There should be something which instantly alarms the required people and then the required safety or the equipment reach or the people reach, the resources reach to the place instantly. So if a GPS tag, if it is to its miniaturized size, is able to uh, is uh, is worn by a by a maintenance person, it interacts continuously with the LoRa gateway and with the cloud through IoT, and it throws back the signal to the safety personnel, to the factory manager, to required people, managers, who continuously are able to see on a screen in the factory or on their mobile devices or in the emergency room on the laptop screens, desktop monitors, that there are 10 people working at these 10 sites, all are safe. They are moving from one place to another safely. If something happens, the person must be able to immediately press a panic button, which you can see on the right hand bottom side, which is not very difficult for a person to press because it is so uh, easy to operate, so that a person immediately on the safety emergency room able to see a red flag and immediately ambulance rushes. So this is one very small example wherein you can see a small architecture, the device, a person working, which will take care of people, which will take care of factory compliances as well as the environment. Now, it's a perfect digital twin because, I mean, I have not yet talked about the digital twin, but it's a perfect Industry 4.0 example wherein it closed loops. Now, if the cloud is able to also analyze the data further, that it was this date, this season, this person, this equipment, this is what it happened. And then it analyzes and creates via deep learning techniques that during these conditions, we must take necessary precautions. So when a person enters next day, it should get a signal that, look, this is what it happened. You must take care of this. And accordingly, it throws a signal back to the equipment manufacturer that, look, during these conditions, we found out that this was an analysis, root cause analysis. Can you tweak your product design? And the product design modification takes place. And it is readily available for the next set of customers. This will be a digital twin. Today, what happens? The root cause analysis takes for 2-3 months. There is a big negotiation between the equipment manufacturer and the factory people. After a year or so, the equipment manufacturer agrees that yes, this was the issue, we'll change the design. The design change takes place after 6 months, so 1.5 years, 2 years for the product to come into the market. Whereas if it continuously accesses data from its customers and it throws back to its design team, and design team is continuously analyzing the data that it is receiving, and it changes and tweaks the design, and immediately the next lot that goes on its shop floor, let's say compressor or a generator set, Kirloskar engines, Cummins, so on and so forth. And they are changing, and continuously the change is taking place on physically on the shop floor. Look, within 3 months, a new product can come into the place, as against 1.5 years or 2 years. This is what is a digital twin. So this is one of the examples for a factory from the point of view of safety and environment, utilizing GPS tags, LoRa, mobile apps, and AWS or Azure clouds. Is it pretty clear, team?
Yes, sir.
Thank you. Let me go on to the next. Now let's talk about the maintenance. Typically, a maintenance has been through a pyramid of its evolution. 40, 50 years back, it was a reactive maintenance. Failure, run after failure. Then people started talking of TPM philosophy. Preventive maintenance. Can we predict and prevent? So first, preventive came into picture. So at certain frequency, people used to go and check certain parameters. Then it was condition-based maintenance with sensors and MES displays. That centrally MES display was taking place, that there is a temperature, this is a temperature, this is pressure, this is flow, this is vibration, and so on and so forth. And then accordingly, if it entered into a red zone or yellow zone, they used to take actions. Then in its real sense, predictive maintenance came into picture, wherein automatic decisions started taking place. Prediction started taking place with the help of some data analysis. But then today, we are talking of cognitive data analytics. What does cognitive means? It's not prediction. It's in real time, currently, as the environmental conditions are changing, continuously deep learning techniques are being utilized by the data analytics team, and they are continuously feeding this data and evolving their data analysis algorithms. And at one point of time, it becomes so cognitive that it throws back the decisions and it also corrects the system on its own. This is what is autonomous state. So for example, if for maintenance of equipment, there are advanced sensors which are interacting with through LoRa, long-range communication devices, through IoT gateways, with cloud, and with the deep learning algorithms that have been fed. They are continuously monitoring and changing and tweaking, mapping and remapping its deep learning algorithms at the back end. What would happen is that, as I talked in my earlier slide, the maintenance would become more and more autonomous, wherein the data would be directly fed to the supplier, and supplier design team would take calls based on this data that is coming up to them, and they will be able to get some insights ready.
Hello, sir. Hello, sir.
Hello.
Yes, sir.
Yeah, sincere apologies. There was a power breakdown.
Okay, okay.
But I had already provided hotspot connection from my mobile, so it took some time to connect. I hope you are able to see my screen.
Yes, sir. We can enlarge it.
Yes, I will.
Fine, sir.
And this, yeah. So, and this is how a digital twin architecture would look like wherein the sensors are acquiring data, it is sending the data through IoT gateways, the decision making is autonomously taking place, and the faulty conditions are being turned into normal conditions. And in turn, it is also being fed to the original equipment suppliers. Their design team is also taking care of all these things. This is how actually the predictive maintenance can go to cognitive data analytics and cognitive maintenance. And this is one use case which is typically being also implemented at few places in some of the bigger industries. Now let me go on to the next slide. Dr. Shanmugesh, a sincere request, if you feel that there is a difficulty and lag in communication, I would close my video.
No problem, sir. No problem. I'll intimate you, sir.
Okay. Okay. Uh, Typically, a predictive maintenance LoRa infrastructure would look like this. There are end nodes which can be fitted onto equipments. You can see a picture down below. It communicates with the LoRa gateway. Now, the gateway is just a symbol. You need not have a big tower. Any typical factory, a big factory, would have different towers for communications already fitted. We might one can use them, and we can use them to fit some of those LoRa gateway devices on those towers itself. So that's a bridge, MQTT broker, and then it goes to the LoRa server and so on. It closes the loops. It is taking continuously the data in and out, communicating with the cloud, and then the final communication can be seen by the management on big monitors, on laptops, on mobile devices, so on and so forth. This is how one can see whether the run charts, the values, different torques, power, smokes, if it is an engine testing, production levels, everything. Everything can be seen, and autonomously the decision making might take place if it's a digital twin, or if it's automatic, the production supervisors and managers can take calls. Now let's talk of the autonomous production planning. We talked about that the production planning based
I think signal loss, sir.
Can you hear me?
Yes, sir.
The power is back, seeing it. So
Okay.
this is what we need to take care in industry 4.0. So the planning scheduler is continuously accessing
Sir,
this data from the
we are not
bottom
getting any.
three
Can you share your
databases.
screen?
Let me again reshare this. It might have lost. It is showing me that it is not giving me a signal that it has lost transmission.
You
Are you
can
not?
stop sharing and then again share this.
Let me do that. It's taking time, Dr. Shanmugesh.
Okay, sir. Okay, sir. Participants, sorry for the inconvenience.
If you're able to hear me, I'm not sure
Yes,
why
sir.
it is not sharing the screen still.
Otherwise, you can leave it and rejoin once again, sir.
Let me try this. I think it should start now. Let me see. No. Are you able to see now?
Now, yeah, okay, sir. Fine, fine.
I've shared my screen. Fine. Right. We were here. Now
Yes,
is
sir.
it on? I have
Fine,
just
sir.
expanded the screen. Okay. We were here. Sorry, guys. Let me start with the presentation. So the planning scheduler has at the back end algorithm and the coordination engine, and it is taking data from all the necessary resources and continuously learning with the deep learning techniques. And this is how it gathers data from all machines, from the different communication modes like writing SOPs and so on and so forth, because that is also very important for it. And ultimately, it is able to run the production. What is required for a production for a scheduler is visibility of parts that are required to build a product, and then in which sequence it should launch it. So for the visibility, it should have the BOM, the bill of material available for all the products, which must be integrated to an ERP system. In this case, for example, it is SAP, and then user interfaces, Java software enabler, which in which if you write algorithms, continuously get data of BOM and interact with ERP system, you will be able to continuously see the parts that on real-time basis which are at shortage, which are available. Then once you are able to see that, you can sequence the variants so that the line runs smooth, because there are different timings for different variants. Let's say for car, if it's Wagoner, if it's something else, Alto, and on the same line, there are different timings. So which sequence should to be followed so that the line runs smoothly and there are no big gaps. So genetic algorithms are used nowadays to create sequencing, which will be throwing the manufacturing constraints to the scheduler, and it will be able to analyze so that the critical time comes down, productivity goes up. And these are how typically the algorithms are written in genetic forms using some Java infrastructure. And then you can have the sequence of launching on a line. So there are various other algorithms also available. Genetic algorithms are very common nowadays for some complex scheduling. This is one of the examples of autonomous production planning. Let me talk of now extended reality. Little bit busy slide. Why extended reality? Because a 3D drawing is perceived on a screen, and one can see it on a screen, either tab or laptops or on mobile screens. you can extend the image, which is in 2D to 3D in its real form. One can use glasses, like Google glasses were very common. One can use tabs or perception devices. Augmented reality, how it works? When you focus a tab on a particular QR code or on a material, the material gets captured and the material, the tab at the back end, the camera at the back end, will cross-check the image with the image that is available in the CAD drawing. ProE, ANSYS, the various different tools that are used today in the industry. It matches it to 100%, and in no time it gives details of that part, whether the part is rightly being picked for that car or that tractor or for that pharmaceutical tablet, the chemical, or it is not so. What are the parameters? Whether the chemical, the physical, the mechanical properties are right. What is the quantity? Whether the quantity is right. Whether this is what is the first to be picked up and not the last to be picked up. All those details can be thrown on the tab or on a screen. Once the person focuses that tab, the camera, on a particular product. This set of software is available within the tab. One can buy it, subscribe it from different available sources in industry. Today there are PTC, then Infosys, the Geometric. These people have developed these softwares. One can buy them, implement them. For schools and academics, these softwares are available at discounted prices. The prices are very low. For prototypes, these softwares are available at free of cost also for some period of time. Very powerful media. And this can be utilized either with the Google Glasses or with the tabs or some other devices, wearable devices, even the smartwatches. Google Glasses we will talk about in the upcoming slide, but then these reality devices can be used for training your new people. For training, many times we have to put the people online, and then there is a safety issue, or people might do some mistakes and a quality product might get hampered. If these devices are used in training room and they're able to feel this, see this and feel this on a tab, they will be trained in much advanced fashion. And when they go on to the line, they are very well versed with the product and the line infrastructure. So it will be not very new for them as against today's scenario, wherein there is no extended reality. So this can be used for training, for safety purposes, and for quality build products. This can be used in material planning, wherein a person focuses, it reads that it is a correct part, it takes it and ships the part to the line, a correct part, in no time. That's also again another advantage. On work assembly line, on machines, if these cameras are hung onto the line, it will automatically capture the image, and it will immediately throw what sequence to follow for operator. That this part should be first handled this way, this should be tagged this way, then this should be placed in this manner, not on this machine but on that machine. So it will always avoid all the wrongdoings by operator. And then the real-time displays of what is happening on the line. And that's the biggest advantage for a management or a leadership. So this is a very powerful media. Real-time and real use cases are already deployed at the factories for safety, for training, for work and assembly instructions, and in some cases prototyping. And I will show you some use cases in the following slide. The middle picture that you see on the top, a person holding a tab, iPad or a Samsung device or a Nokia device focus it on some product, and you will get all the information of that product on your screen. And then you can take a call whether it is the right product or not. Benchmarking is done by various universities, colleges. Colleges buy some certain engines. Now, if the the student want to see whether what child parts are there, simply focus it on the QR code. The QR code will read it. It will tell you immediately that this is the cylinder bore, the bore has this size, this is a piston, this is what is it, the size, and this is how it looks like. You just go on scrolling on the screen and you will be able to see, and you can Chromecast it on the bigger screen. You can scroll it, you can see everything. Than opening up of an engine, you can see everything. So a big labor of opening an engine for months and then seeing it can be avoided. And you can teach large number of students in some days or weeks. This is a very powerful media. These are actual use cases which are being implemented in some of the colleges or by the industries for training purposes. You can see on the left hand side, bottom side, the bigger picture wherein there is the infrastructure piping, then the digital and analog displays. You just focus on them and you will be able to see whether the filter is working properly, the flow rate is okay, the temperature is okay, the pressure is okay, not okay. Immediately you will be able to take a call and the data can go to the maintenance person. Immediately the maintenance person will come and he will do the maintenance. These are powerful use cases already implemented in industry. Couple of other, now the Google glasses. See, these are very popular. Are they successful? Technically, yes. But what is the difficulty today? Safety. When a person is wearing it in a factory and he is moving here or there, or people are moving here or there are some other material movement taking place around him, he might miss noticing them because he is wearing a goggle. And on a goggle, you are able to see some of those 3D models in real perception models, in perception media, whereas he might overlook some of the material movement that is taking place around him. And that's where a bigger difficulty is here. So the eye wearables technologies for safety concerns are not getting yet promoted at a wider level. Still, the research is taking place here on the eye wearables. But the other wearables are getting more and more popular, like the waist, the hand media, smartwatches, and the tablets and other things. As I talked about that the servicing and maintenance, you can use this very powerfully, and very successful use cases are already implemented in industry. Let me talk of collaborator robot. We talked of, as I said in my first two slides, I will talk of two critical Industry 4.0 technologies that have been evolving under Industry 4.0. One I talked about extended reality, another is collaborator robot. Collaborator robo as against the industrial robo, you can see on the right hand bottom corner wherein I have crossed it with a wrong sign. It requires fencing, lot of safety parameters to be taken care of. If wrongly some person enters into and the robo hits him, there can be a very fatal incidents. The collaborator robo, in contrast, is far safer because of the special sensors that are used. The sensors are able to sense the vibrations in all 6 degrees in multiplication, and it acts like any other human being working alongside. So people working and people are checking some things, and the collaborator is loading and unloading the heavy parts and products. It is also inspecting, it's also torquing, it is also dispensing the fluids, so on and so forth. Pick and place dispensing, inspection are three major applications that today industry has adopted with collaborative robots working on the line. Even if it touches or comes in nearest proximity of a millimeter from a human being, it would immediately slow down and it will not hit the person. Even if person wrongly hits it, the robo might have come to a standstill. It's only because of a person's hand speed that the person might get a hit on its hand, but not because of robo. This is what is beauty of collaborative robo, available at cheaper costs in industry from 20 lakhs, 15 lakhs to 50 lakhs, a crore or so as well. Very bigger applications taking place. One can fit camera at a time. A single collaborative robo can be used for multiple applications. Camera installed, it is continuously inspecting and checking whether the right person is working on the line, certified operator is working on the line. In turn, giving signals that okay, turn, there is a cassette, like it is on the CNC machines. Turret, in simple terms, turret. The turret rotates in few degrees, torquing takes place, rotates, pick and place takes place. You can load a collaborator robo with multiple fixtures for pick and place, for dispensing of sealants, of greases, oils. It can torque, it can untorque, it can inspect, so on and so forth. One single collaborator robo. Depending on speed of a line, you can have multiple robots on the line as well. On the top right hand corner on the slide, you can see a moving collaborator robo for material handling. Again, a successfully implemented use case on lines nowadays. But when I say successful, whether it is collaborative robo, whether it is extended reality, whether it is a moving robo, it's for those organizations or factories who have invested and who have explored different technologies, we have put resources on data analytics, and deeper algorithms are being built. But it has not been successful for those organizations who have not yet thought about this, as I am putting it and presenting it to this audience. So it's yet being explored by many factories still. Hardly a percentage of it or so is implemented today. Again, Internet of Things comes into picture, speed of communication comes into picture, resources, brains are required, and that is a real bottleneck today in industry. Smart vision systems, smart cameras. The fixture comes near to the bore of a cylinder. It inspects the bore for its different parameters. Then it also catches a defect, a small dent of a size, area, width, and height, whether it is within range of drawing parameters or not. It takes a decision. It says okay, not okay. And then also it throws a CPK statistical statistical chart, and it says whether it is okay or not okay. For a camera to be very, very smart, it has to continuously capture images, 2000, 4000 images of defects of the bore diameters. And based on the sustained, continuous, consistent capturing, the deep learning techniques will evolve the algorithm to a status wherein it will be real smart and 100% always give a good result, whether it is bad illumination area, good illumination area, whether it is a winter season, whether it is hot season, whether it is rainy season, based on the environmental conditions, the light conditions change inside, all those can be fed to the camera, backend algorithm, it is continuously learning, deep learning, and then it comes to a stage wherein it is real smart. It can reduce all these biases, environment biases, and still give you 100% accurate result. Enormous exploration, but again getting successful in some of the industries. Not every applications, some applications. It will take time to evolve. Deep learning again is very important in this case. Smart kitting, near field communication devices, cameras, virtual reality glasses, augmented reality handsets, worn by an operator. As you can see, operator holding a trolley. He moves through the warehouse. He is scanning. As he moves, the wearable devices captures the correct part. It immediately signals on the trolley. A light will glow up. Operator will know that this is a part that it has to pick. It will pick a right part. Once it picks it, the photo sensors will give a signal, yes, you have picked a right part. For it to say that, yes, have you shipped it? When it ships it to the assembly line also scans it and it says, yes, you have delivered a right part. This is how a perfect close looping of smart kitting takes place. So it will improve quality, it will improve productivity, also safety. Near field communication scanning is one of a very common technology that can be used. Cameras can go little costly. AR handsets still can be very cheaper. We can use based on how much data we want to analyze, what is the speed of the assembly line, whether it is in seconds, whether it is in minutes. Based on that, we can choose different technologies. Shipping efficiency, again, we can use wearable devices, handheld devices, scan it. It will immediately tell whether what part it is, whether the part is right, the quantity is right, and again, the logistics speed can be improved. So this is on the shipping efficiency. Now, this is where I talked of all the digitized IoT devices and how the architecture should be there in a factory so far. If it is clear, if there are any questions, I would like to pause here, and then I would come on to the last set of slides, and I would talk about how universities or colleges like Vishwajyoti Engineering College can utilize this as an opportunity.
Any queries from the audience? I think everybody is
I hope I have not bored enough for them to sleep.
No, sir. It's a good going, sir. Hope we can continue.
Okay, if it is so, let me. Yeah, thank you. Now, a college like Vishwajyoti College of Engineering, how you can utilize this as an opportunity? I have tried to put it in a couple of slides. See, as I talked about, and if you have understood in its clear sense, a small laboratory can be set up by a college like your college, Dr. Shanmukesh, wherein it does not cost so much, but then we can utilize also the available setup that is there typically in any engineering college. There is a big workshop, machining workshop, welding workshop, there are small paint workshops, there are hydraulic labs, there are pneumatic labs, there are PLC labs. There are applied mechanics labs, civil engineering has its own lab, electrical infrastructure, electrical engineering department has its own infrastructure. IT department has its own infrastructure with different integrated circuits and so on and so forth, many things. We can utilize the same setup at one place, form a small, either it is product-based or a process-based line. When a small product flows from one end to another, or it need not be. We can build some collaborator robots inside, or we can buy them. As I talked about that, the costs are coming low and low. In the prelim cameras can be also bought, which are available at 1.5 lakh rupees as well. And this setup can be installed in a workshop. And you can start analyzing, capturing more and more, like there are engines, there are vehicles which are available in a lab, particular in an engineering college. Start capturing the data, start analyzing, put your computer department students or the IT department students to start building algorithms. You can organize hackathons so that they build, and they wherein removing different environment biases, making it more and more 99, 99.5, 99.9, 100% accurate. Build those algorithms. You can put some small Zigbee devices, Bluetooth devices, NFC tags, already RFID tags, and use PLCs, CNCs, which are available in the machine shops, workshops. Make them more smart, capture the data. Again, the data analysts can come into picture. IoT gateways are available at very cheaper cost, 50,000, 25,000. Siemens, Allen Bradley, and others, LoRa gateways as well. And you can create this infrastructure within a factory. You can have a small subscription with Amazon, Azure, or some local cloud computing and the service providing factory companies, organizations at cheaper costs. And this infrastructure, start exploring this to your use, day-to-day use, which anyway 12 months in a year is continuously happening at any college. Once you acquire this, you can really go outside and tap some of the small factories, small firms, and you can start working on the projects wherein you can digitize their small stations. This will really make an engineering college like yours a smart college, and you can offer these services to small industries, thereby making the industries more and more smart, from a station to devices to assembly lines or so, wherein you also acquire knowledge and you learn and you also become smart. And this is how you can participate, you can explore, and you can learn more and more and become more smart. And this is what is also in future going to be a revenue sharing model between industry and college, as well as the students will become more and more learned when they go and they become ready to go into industry. And also the college can acquire a reputation across the fraternity that this is a college which offers this. This is a college wherein there is a talent. And this is how I would propose that one can partner with some of the consultants outside, freelancers outside who know about this media, who know about this field, this topic a lot. They have worked in an industry, and then utilize their consulting power to enhance your own technical knowledge base and utilize it for an industry where an industry partnership goes stronger. This is what I would suggest to college like Viswajyoti College. You can ponder upon this, you can think upon this, and you can explore this further. With this, I come to an end of my presentation, dear audience. Thanks, Dr. Shanmugesh, Dr. K.K. Rajan, for inviting me and offering me this opportunity. It was a privilege presenting to this respected group of faculty members. And we can also grow this partnership going further from here. I am open for that, and we can always be in connect and touch. Thanks a lot for hearing me patiently. If any questions, I'm ready to field. I would definitely not be a very expert member wherein that I can talk on algorithms or some of the electrical systems also, but I can definitely talk about Industry 4.0, the architecture, the digitized connect and analyze space, and how the ideation can take place. What are the different exploration opportunities available? And we can always talk about that. And I'm ready to field those questions over here. Thanks.
Thank you, sir. Thank you for the wonderful session on the industry perspective. So now any queries from the participants? Participants, please feel free to ask any queries. Please try to utilize the expertise of Jain sir.
I hope the topic was quite self-explanatory. That is what I can hope.
Sure, sir.
And if it is so, that I can have some questions.
Any queries, please?
In the meanwhile, I'm just trying to take a photograph of Dr. Shanmugesh.
Sir, if no other queries, can we wind up, sir?
Yes, thanks a lot, Dr. Shanmugesh. And I think, as I already talked about, sincere thanks to you and your college and your principal. Please convey my best wishes to Dr. K.K. Rajan.
Sure,
And thanks a lot, dear professor. I forgot your name who introduced me. And thanks all the faculty members who were present here.
Thank you, sir. So let me invite Mr. Arun Kiar for proposing the vote of thanks.
Okay. The session was related to the Industry 4.0 and its relevance in manufacturing. And the spokesperson has started with the digital twin and how actually the human being evolution is the most perfect example of digital twin. And it was a nice, interesting class, especially in my point of view. Extended reality and collaborative robotics and autonomous production planning, predictive maintenance, etc. So actually, it's all of you get knowledge from that areas, and also the last section that how we can set up a industrial for 4.0 lab in our engineering colleges with reduced cost and effectively. That was a nice information from you, sir. Actually, I express sincere gratitude to, on behalf of all participants and our department of HICT mechanical, and I think this class was effective and beneficial for all the participants, those who are attending the session. So once again, I express sincere gratitude to the spokesperson, Mr. Uday Amit Joshi sir. Okay, thank you, sir.
Thank you, Professor.
Thank you very much, sir.
Thanks
Thank you very much. Hope to see the future also, sir.
Thank you.